This video is for Chapter 3, Section 4, and it will be covering the polygon interior and exterior angles. Previous to this lesson, we were studying triangles and their interior angles that always added up to 180 degrees. Today what we're going to do is take a look at what about shapes beyond a triangle, quadrilaterals, pentagons, shapes that have more than 3 sides, and how the sum of the angles inside of a triangle can help us understand the sum of the angles inside any shape. So, first of all, let's define polygons. The root here, poly, means many, and when we say polygons, it actually stands for many sides. So anything with 3 or more sides is a polygon. 2 sides is not enough to create a figure. So, a polygon is a closed plane figure with at least 3 sides. These sides intersect only at their endpoints. There's no crossing or X's within a polygon. So, we have a polygon here. Here's one of its sides. They are segments between 2 points. And here's a vertex. Now, when we name a polygon, for example, this polygon I named Bruins. The vertices are listed consecutively. You need to pick one vertice as your start point and then go around the shape. Clockwise or counterclockwise does not matter. I chose to start at B, and then I say B-R-U-I-N-S, polygon Bruins. This has 1, 2, 3, 4, 5, 6 vertices, so there are 1, 2, 3, 4, 5, 6 sides. This would be a hexagon. Now, as we move on, you can name these different ways. I could have gone S-N-I-U-R-B. I could have gone clockwise, counterclockwise, does not matter. What would not be allowed is to say B-I-S-U-N-R. We cannot go across diagonally. We have to create around the shape. Next, we have a diagram here that shows 2 different types of polygons and these dotted lines, which are diagonals. So first I'm going to define what is a diagonal. When I describe a diagonal of a polygon, that is a connection between 2 vertices that are not part of the shape. So connecting this vertice here to this vertice, that's not a diagonal. That's a side. But if I connect this vertice to this vertice, that is a diagonal because that is connecting 2 vertices that are not already connected together. Now, in this shape, I actually have all of the diagonals drawn in. Here and here. It's already touching these 2. Those are sides. So this vertice has 2 diagonals. This vertice has 2 diagonals. All of the diagonals are drawn here. Something is different in this picture. I have not drawn all of the diagonals. There would still be the one connecting here to here, maybe one from here to here, there to there. There's one here and here. But there are these 2 diagonals that are very critically different than all of the diagonals here. These 2 diagonals occur outside of the polygon. So we're going to have 2 new vocabulary words. One to describe a polygon in which all of the diagonals are inside the shape versus a term for a polygon where the diagonals are, or at least one diagonal is outside the shape. The terms are convex and concave. A polygon is convex if not a single diagonal contains points outside the polygon. It is a nice convex polygon. Concave is if at any time there is a diagonal that contains points outside. So this kind of concave is meant to mean sunk in or has a dent in it, like this portion right here. There's 2 points on this polygon. But if we have one diagonal that goes outside the shape, it is concave. So those are some of our definitions for today, and now we can get into the material. I'm about to draw this chart over on the sideboard, and we're going to go through how we can look at a polygon, how many sides it has, the number of triangles I can form inside that polygon, and then the sum of the interior angles. So let's head on over to the sideboard and we'll work on that. Okay, so here's the chart that we were asked to create. We have a set of polygons. It says polygons here. I've got a triangle, a quadrilateral, pentagon, hexagon. And then I have the number of sides, so let's go ahead and fill that in. A triangle has 3 sides, 4 sides for the quadrilateral, 5 for a pentagon, and 6 for a hexagon. Then we have this weird one down here, n-gon. Well, n-gon means n sides. Okay, n. I don't know how many sides that is. Could be 20, could be 5. Then we have how many triangles are formed. Well, most simply, there's 1 triangle formed. But then the problem here is that there are no triangles in the quadrilateral. So what we're going to do is we're going to create diagonals. And we don't want any diagonals to cross each other. So I'll try to draw one. Now, there's one more, but I'm not allowed to cross a diagonal. So I think this is it. And notice it creates 2 triangles. If I was to add up the angles of all the triangles, it would be all of the angles inside the shape. So 2 triangles have been formed. Let's try this for the pentagon. I'm going to use the top vertice and connect it here. And I'm going to use the top vertice and connect it here. Now, I cannot connect any more diagonals. If I do, I will cross over one of these. I can't connect here, can't connect there. So that's it. Without overlapping diagonals, got 3 triangles. Awesome. So then let's figure out, let's try a hexagon. I'm going to go ahead and work off of this corner here. I'm going to go straight down to that one. There's one. And there's another one. And there's one more right there. That's a terrible diagonal. Let's try that again. Okay, good enough. So now I can't overlap. So I have 1, 2, 3, 4 triangles. You guys, at this point, I'm starting to see a pattern. I want to be inductive here. So 3 sides, 1 triangle. 4 sides, 2. 5, 3, 6, 4. 7, 5, 8, 6. How about n sides? Take a moment and think about it. Pause the video if you have to. N sides. Well, 4 is 2 less than 6, 2 less than 5, 2 less than 4, 2 less. N minus 2. So no matter what the shape is, there will always be n minus 2 triangles. Now, I know that inside of a triangle, the sum is 180 degrees. But in this case, there are 2 triangles. If I add up all the angles, it makes up the quadrilateral. So there are 2 180 degrees, which equals 360. In this case, there are 3 triangles, 540. We have a nice little pattern going. 180, 360, 540. We just keep adding 180. 4 times 180 equals 720. The question then becomes, what fills in our final blank? What about the n-gon? Any number of sides. Well, there are n minus 2 triangles, and for every triangle there is 180 degrees. So n minus 2 times 180 degrees. I could use this if the polygon had 10 sides. I would say, well, 10 sides is going to have 10 minus 2, or 8 triangles. 8 times 180 is the total interior sum, the total of all the angles. We're going to use that information and what we just did on this chart to go back to our lesson now and look at what is called the polygon interior angle sum theorem. Okay, so we just got done putting together this chart. One of them was a quadrilateral like this that had 4 sides, two triangles formed, and it's added up to 360 degrees. From this, we were able to make a determination of what is called the polygon interior angle sum theorem. The sum of the measures of angles inside of a polygon is equal to n minus 2 times 180, where n minus 2 represents the number of triangles, but n is equal to the number of sides. N equals number of sides. Very important distinction here on the slide. N minus 2 is the number of triangles that were formed. We multiply this by 180 to get the total sum. Now here's an example problem of how we could utilize this material. We have one missing angle. I have three 90-degree angles and one missing. I have 1, 2, 3, 4, 5 sides. So there are two things I can say. 90 plus 90 plus 90 plus 135 plus x. That there equals the total of all 5 angles added together. But we have a formula. The total sum is also equal to 5 minus 2 times 180. So we can set these equal to each other because the sum of the angles, actually adding all 5 together, should equal the sum formula. So I can now put all this together. 90, 90, and 90 is 270. 270 plus 135 is going to be 370. Plus 30 is going to bring us to 4. 405 plus x is equal to 3 times 180. Well, 3 times 180 equals 540. The 5 angles inside this shape must add up to 540. I already have 405 of that, so I'm going to subtract the 405 and end up with x is equal to 135 degrees. Now, this is not always the case that whatever is here will be here. That is just specific to this type of problem that I created. This is the method for how to solve for x using the polygon interior angle sum theorem. You first find what all the angles add up to, then you actually find the total of what they are supposed to add up to. Now, a second theorem that we have that we are not going to produce a chart for is the polygon exterior angle sum theorem. Now, the exterior angle sum theorem says that the sum of the angles outside of a polygon will always add up to 360. So let's take a look at, first of all, what an exterior angle looks like. So if I draw this triangle here and extend these sides, here are some exterior angles. Angles 1, 2, and 3 will always add up to 360 degrees. So the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 is equal to 360 degrees. Now, for a triangle, there are only 3 exterior angles. However, this shape is not a triangle, and there are 4. 1, 2, 3, 4 exterior angles. Well, just like our previous example, what we need to do is add up the angles. I have 115 plus 95 plus 71 plus x should equal some form of total. Well, the good thing is the exterior total is always 360. Not n minus 2 times 180. It's always 360, no matter what shape. So, we got to add these together. So this is going to end up being, when we have the 115 plus the 95, so we're going to have 210 plus 71. That's going to end up being 281 plus x is equal to 360. We're going to subtract that 281 that we already have from 360, and we're going to end up with x is equal to, well, sorry, this is supposed to be 281. So that's going to be 9 there, and that's going to be 79, and x is equal to 79 degrees. That is how we use the exterior angle sum theorem. One good thing about this theorem is it always adds up to 360, no matter what the shape is. Now, a few other definitions for us. First of all, an equilateral polygon. Equilateral. The word lateral means sides. We learned this from an equilateral triangle. So equilateral polygon means all the sides are congruent. If we have equiangular, we have a polygon that has all congruent angles. Now we have to be really careful here, because just because we say equilateral does not mean that it's equiangular. For example, I could draw this shape and where all 4 sides are definitely congruent. This is not equiangular. This is equilateral. I could also draw this shape in which all 4 angles are right angles. This is equiangular. But it's not equilateral. So the question is, what term will we use for the shape that puts these two together? Now hopefully you can look at these two shapes and we start to think, I know what this is going to look like. I know what shape is there. If we put all the sides together and all the angles together, we're going to have ourselves a square. All 4 right angles, equiangular, all 4 sides congruent. So we need a term for this. This is a regular polygon. We didn't need this term for triangles because equilateral triangles are equiangular. But that's not the case when we go beyond 3 sides. So this is a regular polygon. Now we have a special name for that one, square, but we need to know regular means all sides, all angles congruent. This would lead us to a question like this. How can we put everything together that we've learned from today's lesson? Find the measure of an interior and an exterior angle of a regular octagon. Alright, so this is our final example for today's lesson. Find the measure of an interior and exterior angle of a regular octagon. Let's get started. First of all, I know I can find what all of the angles add up to using the interior angle sum theorem. So, n, which is number of sides, octagon has 8 sides, minus 2 times 180. 6 times 180 is 1080. So all of the angles inside the octagon will equal 1080. Well, there's my octagon. 1, 2, 3, 4, 5, 6, 7, 8. No surprise there. 8 sides, 8 angles, octagon. All 8 angles will add up to 1080. So 8 interior angles equals 1080. Divide both sides by 8 and we have 135 degrees. And we have found the interior angle of a regular octagon. Now there might be multiple approaches to find y. Some of you might already be watching the video and thinking, I can find y because x and y make a line. We're going to come back to that. Rather, I would like to find y without x. Well, all 8 exterior angles are also equal to each other. So, here's a y, here's another y, here's a y, here's a y. There is one exterior angle at every single point. So there are 8 exterior angles, and they always equal 360. This was 1080, but the exteriors are always 360. Exteriors are actually easier. Divide by 8, we get 45. We can now check to make sure this work is correct by saying x and y are supplementary. They form a linear pair, 2 adjacent angles that add up to form a line. Well, then they're supplementary. They add up to 180 degrees. Our answers were 135 and 45. That deserves just a big check mark for us. We can either find exterior, then use this supplementary part. We can find the interior, use the supplementary part, or we can find both and check our work. So that's the culmination of putting together all the terms for today. The polygon interior angle sum theorem, n minus 2 times 180. The exterior angle theorem, they always add up to 360. Regular, meaning all sides and all angles are congruent. That's it for Chapter 3, Section 4. And this is intended, and you can now approach the assignment off of Chapter 3, Section 4.